Hello, peer reviewer. My name is Elizabeth Williamson, and this is Lab 4 Oscillations. In this lab, we will examine the motion of a mass swinging in an arc while oscillating on a spring and the energies in the system. We will first start by talking about some of the basic concepts and formulas. Included in this lab is the position update formula, which is R final equals R initial plus average velocity times delta t, and the velocity update formula, which is velocity final equals velocity initial plus net force over mass times delta t. The mass of the object is also 0.402 kilograms. These will allow us to model the proper motion and speed of the object over the course of time. Also included are the gravitational force, which is mass times negative gravity, with gravity being 9.8 meters per second squared, and the spring force, which is negative spring stiffness times the magnitude of L minus L naught times L hat. By utilizing the distance from the attachment point to the object, which is L, and the period of oscillation, which is 1.651, we can find spring stiffness equaling 5.82 newtons per meter and L naught equaling 0.023 meters with the presented methods. Lastly, we utilize the energy principle to find kinetic energy, 1/2 times mass times magnitude of velocity squared, gravitational potential energy, mass times gravity times delta height, and spring potential energy, which is spring stiffness times the magnitude of L minus L naught squared. Since the energy of the system totals out to 0, we can add these energies together as the work to represent the total energy of the system. I will also briefly show the code used for the model, where you can see that the spring stiffness, L naught, L hat, S, position and velocity update formulas, and all of the energy formulas were placed into the code to output the motion model and show correct oscillation of the object. The object's initial position of negative 0.120 in the x direction and negative 0.634 in the y direction was also input, as well as the mass of the object. Here is the original video from Tracker compared to the computational model from GlowScript. The GlowScript model is slightly different from the original data, as seen by the model only oscillating in one direction, whereas the original changes direction as it slows down and speeds back up. This is the graph from GlowScript modeling all of the energies during oscillation. The gravitational potential energy and the spring potential energy move opposite of each other, but almost equal to each other, which makes sense as net force equals the force of gravity and the force of the spring added together. We can also see that the kinetic energies oscillate twice per gravity or spring oscillation due to the fact that energy is needed to change direction both times over one whole oscillation of the object. This kinetic energy also slows down the object, which creates the change in direction that was seen in the Tracker video, only for the kinetic energy to increase and the object to speed up again. We can then compare the Tracker experiment data to the GlowScript model data. Here we can see that in the X position, the models are almost exactly the same, whereas in the Y position, the experimental data lags behind the computational models data. This is most likely due to a combination of the fact that the period of oscillation was calculated using the data from the X position and human error during tracking of the experimental data. So, is the energy principle satisfied during the lab? If we look back at the energy graph, we can see that the orange line representing the total energy is practically equal to 0 throughout the duration of the model. The total energy is equal to 0 due to the changes in the signs of the kinetic, gravity, and spring energies, which aligns with the formula previously discussed for total energy. This means that we can come to the conclusion that the energy principle was indeed satisfied. As previously stated, the Y position of the experimental data lags behind the model data more than in the X position due to the fact that the model was coded with the X oscillation period. This can further be explored by calculating both periods of oscillation for the X and Y position. Here we can see that the period of oscillation for the X position is slightly faster than the period of oscillation for the Y position, which simply explains why the Y position experimental data moves slower than the Y position model data and why the X position matches so well. Thanks!